starting point for the later content.
Sure, no, I understand that.
Yeah.
Okay. Well, we only have one class left. Well, I only have one class left for the term. I had to reschedule my flights because I was going back through Dubai, which isn't happening anymore. So, yeah, but I'll try to lock in the next class.
All right. Okay, thank you. And have a good weekend. Thank you, sir.
Yeah.
True, that did happen.
I'm sorry, I forgot.
Forgot there was more happening.
Because you were supposed to go to Indonesia, right?
Yes.
And I was like, because I saw you the other week,
I was supposed to go,
and I was like, shouldn't she be?
in Indonesia. In the end, it's okay.
Hey, if they get divorced, you gotta go to another way. No, it's not that.
That wedding was insane. And not in a good way.
The wedding.
Yes.
Why?
It's the most awkward wedding I've ever been to.
The drama
No, but so, okay, so you know, it's a wedding in the jungle of Indonesia. So I expected there to be like a jungle wedding. I said it was like, imagine an American wedding, and an Indian wedding, and a Chinese. And then they made it all awkward.
Were any of them,
No, they were just Indonesian, like,
were the people who were getting married in Asia?
yeah, the girl was Indonesian, and the guy was
You know,
and
about,
then German.
alright.
And then they got, like, the Germans just got invited, so she could film it, so then it could go viral. Just the chat and just every day we keep updated about how viral stuff is going on.
Why?
And it's also like
Really sweet face, what do you TikToks?
she was.
Is she a TikToker?
Apparently she is. I don't know, so I don't know, but like, it's just it's
That
so.
was normal.
That's not normal. Is that something like that?
No.
That's like that's my worst.
It looks like they're in a town hall.
It's so bad. So bad. And then the video of where he takes the first kiss, the worst kiss I've ever seen anyone. You stay super careful, right? And then she looks up and goes like, he's counting down to the kiss. And then he'll just go like this.
Like, no, oh my god.
So bad. And then she turns around, she like hypes the girl up. It's so bad. And then,
Yeah, that doesn't there.
but then they ended up having like this. This is what I wanted, right?
Yeah.
This is what I signed up for.
Did you know the German fella?
No, it's a sign up.
You were the plus one.
I was the, yeah, well, the plus two.
The plus two.
So, but this, like, if it had all been like this,
Fine.
that's super cool. But the other thing, like, I don't know.
Okay,
This was the
so good. Welcome to the lecture. That is lecture what? That's lecture week 8, week 9. So that's our 8th lecture, I think. So in this 8th lecture, now last lecture, we were talking about the multivariate time series, and we started some of the. Okay, wait now, screen first. We started some of the multivariate time series analysis. We talked about the factor armor model. And this factor armor model actually allows us to do a lot of things. So we talk about the forecasting. And then remember in the last lecture, so because I was on Zoom, so this is there's a little bit of technical thing that I basically skipped the forecasting slides. So what I meant to say in the last lecture was actually section 4.4. So I'm not going to repeat that. You can look at the handwritten note there, which is a rewriting of section 4.4 basically. So if you have a factor AR model, so this factor AR model, so if you want to take an L step ahead forecast, then this L step ahead forecast can actually be taken as the best forecast. So the best forecast is actually this, right? The conditional expectation of xt plus L given all the information up to time t for the time series x. So, and this can actually generate the recursive relation between this best forecast, L step ahead forecast, and other other steps ahead forecast. Okay, so the working is basically that the first of all the expectation of future epsilon, of course, using past information is 0. Okay, because we are basically assuming that the epsilons are actually IID here. At the same time, so if you are taking conditional expectation of any past values with past information up to time t, then of course the conditional expectation actually becomes just the constant, okay? Because it's in the past, we know the values of these. And so you create a recursive relation with initial value as the one step ahead forecast like this, okay? So that's what I was talking about in the last slide from the last lecture, all right? So if you have any questions, so just let me know, okay? And then I'm introducing the grandeur causality in this lecture, in this first half of the lecture at least. And then we'll talk about a little bit of examples which may not be in the lecture notes. So let's look at the, let's do this a little bit slower. Okay, so what is grandeur causality? So in time series, of course, causality is very important. So we really study a lot of these relations in essentially to want to know if something, some variables at least, is actually affecting other variables, okay? So, and what's the direction of the relationship? Okay, so that's very in actual analysis of complex time series. This is actually very difficult to establish. But if we're just going to talk about relation, then it may be easier. So let's fix some notation first. So this is the same as in the lecture note. So I have 3 time series variables. Not necessarily scalar, they could be actually vectors themselves, x, y, and z. And we say xt grandeur causes set t conditional on yt. If this happens, if the mean square prediction error of the h step ahead forecast for set t is less than the mean square prediction error for the mean square error of set t again, but without the information on x. Okay, so the h is given here. Now, what are these? What are the notations I'm using? So I'm going to introduce. So where your set th is actually the conditional expectation of set t plus h. This is basically the best forecast, the best prediction for set t plus h with all the information up to time t. What do I mean by all information here? We have 3 different time series, right? So the curly ft, the information up to time t here, is actually defined as the union of this information x up to time t, information of y up to time t, and information of z up to time t. And what do I mean by sigma? So it's a sigma algebra. So I have to write this because, so just by saying union of this information may not be enough. So it's basically, you can think about sigma algebra as basically disseminating the information, okay, of these x, y, and z, okay. So you can take union of them and then take intersection of them, etc., etc. Okay. So it's basically the thorough amalgamation of this information from x, y, and z up to time t. Okay, so that's sigma algebra. So think of all, it's basically all the information of x, y, and z together up to time t. Okay. But what is z minus x? Now, z minus x is very similar. But given it's basically the removal of the information of x, so it's basically just sigma algebra of y, t, and zt. So it's basically without the x. So I set the information set as the union of x, y, and z. And so minus x is basically all the information but without the information on x, okay? So it's basically just dissemination of information of y and z. So sigma algebra of the information of y and z together. So I'm only ever using this sigma algebra notation in this section, okay? And it's basically conceptual, okay? You don't have any real technical consequence. It's basically conceptually, it's dissemination of information, okay? So what is MSVE? So you should have learned that from last lecture. The mean square prediction error is defined as, now you may have learned this in the scalar time series. So this is multivariate, so this time you're talking about the square norm of that, okay? So the square norm of that means what? Means it's basically just the zt plus h minus zt bracket h transpose and then multiply with itself, right? So that's multivariate, since zt potentially can be a vector, okay? And what is the minus x there then? It's the same, so just for completion's sake. So that's basically the expectation of zt plus h minus z minus xt bracket h. Okay. So branch causality means what? So I have given all the definitions here. Branch causality means, so if you're forming a prediction using, so say zt is the target, is the response, and xt and yt are actually explanatory variables. Okay. So if I remove xt as an explanatory variable and then try to predict zt, well, the result is actually worse than including xt. If this is the case, then xt actually is grandeur causing zt. And of course, it's conditional on yt. Yt is always there as explanatory variable. So we say it's conditional on yt. If you don't have yt, it's just zt and xt, then you're not conditioning on yt. So it's just xt grandeur causing zt. Okay. So removing xt as an explanatory variable, the mean square prediction error is actually larger than including xt as explanatory variable. So you include xt as explanatory, then your error of prediction is actually getting less. So conceptually, maybe xt is actually important in explaining zt. Well, at least that's the initial intention. Okay, so for these linear time series models, then the direction of causality usually is fine. But actually, in the end, this is still about just correlation rather than the direction of cause and effect. Okay, so if ZT and XT in general has a complex relation, then usually it means the XT is grandeur causing ZT. The other way around usually is still true. So ZT is also usually grandeur causing XT. So in the end, we actually don't know in general, the direction of causal relation. Okay, so as long as they have a complicated relationship between the two, even if XT is each actually the cause of ZT, if you look at XT and then try to ZT as explanatory, so you will still find that XT is grandeur causes by XT is grandeur causes by ZT. Okay, that's usually the case. Okay, so grandeur causality is most of the time is just for linear model. So we have introduced the vector armor model. So is usually can be applied to vector armor model. And people nowadays improve it to include nonlinear models over just a vector armor model, and to try to make clearer the direction of relation. Okay, so if you're interested, so please search for this generalization of grandeur causality. So there's still, I think, at least a group of people is doing active research on this thing. Okay, to make it as more detecting the actual flow of causality. Okay, over different more general models. But for now, so let's look at our definition of grandeur causality. So I hope the notation really doesn't intimidate you too much, because I'm going to make a very, very simple example. Okay. So let's look at a very quick example. So let's look at this bivariate time series. Okay, so let's say xt. Let's make alpha equals to 0. So that's the easiest. So there's let's say 0.8, and then minus let's say 0.3 yt minus 1, and then plus epsilon xt, and then there's another equation in the bivariate system, so there's xt and yt. Well, this one has let's say just as a simpler let's say minus 8 yt minus 1, and then plus epsilon yt. Okay. So that's the system. And what is epsilon x, epsilon y? So you can define this as a bivariate factor. Epsilon x as epsilon y. So let's say it's so I'll use this notation IID. So IID mean 0 and variance sigma square I2. Okay. So it's a bivariate. So I need to specify. When I specify its mean. So it's both 0, and then the variance, so it's a variance covariance matrix. So is sigma squared times the 2 by 2 identity matrix. So I2, I use it to denote the 2 by 2 identity matrix. Okay, so good. So this one is actually also very related to the I think examination last year, but anyway. So first of all, usually our task is okay. Can you write it as a bivariate system? So if you let set t be defined as xt, yt, then you can write it as a system of just a factor AR1 model with the defined matrix equals to 0.8 minus 0.3, and then this is 0, this minus 0.8. Okay. Then the whole system can be written as set t equals to what, 5 times set t minus 1, and then plus epsilon t, okay? So this is just a factor AR1 model, so the dimension is 2. So epsilon t ID means 0, variance in the square I2. Okay. So if I talk about Granger causality, so does xt Granger causes yt as a time series. And when I say Granger causes, so you're talking about some prediction, some h step ahead prediction. So you need to specify your step of prediction at h equals 1, let's say. Well, you can verify that, of course. Well, you can see that what is xt plus 1? Xt plus 1 is 0.8, xt minus 0.3 yt, and plus epsilon xt plus 1. Right? So therefore, so let me use the same line here. Your xt bracket h is 1 here, your xt bracket 1 will be just 0.8 xt minus 0.3 yt. Okay, and that's the information of both xt and yt together. Okay. So if you want to establish Granger causality, so you need to, in here, x is the response, so you need to remove y. Okay? So you need to consider minus y with information up to time t of your one-step forecast, okay? It should be the other way around, sorry. I should talk about yt Granger causes xt. Sorry about that. That's my intention. So this yt gradual cos as xt. So xt as the response. So you need to calculate this one step ahead forecast, both with and without the yt as the explanatory potential explanatory variable. Okay. So here, so you can calculate the expectation of .8 xt minus 0.3 yt and plus epsilon xt given. So given is minus y, so it's just fx basically. So you actually don't exactly know its value, but because you don't know how to calculate the yt given information of x up to time t. But of course epsilon xt plus 1 is our ID, so given whatever information up to time t, so it's still 0. Okay. The information on xt actually, well, it does include some information from yt. You look at the equation. So you should be able to calculate this expectation, but it certainly won't be 0 in general. Okay. Because information of x does include some information on y, just from the first equation, right? So you just don't know how to do this. So I'll stop the calculation here and consider another scenario.
So in this case, could we say that it Granger causes xt?
So in general, so without y, so this is usually non-zero. Okay, so this is usually non-zero because information, as I said, information of x is actually containing some information on y. It's just from the first equation for xt. Okay, so if you calculate the mean square error, so this will be the expectation of xt plus 1 minus x minus yt 1. And that will be what? That will be expectation of, so 0.8 xt, so that's a constant that can be cancelled out. But 0.3 yt cannot be, right? So it's minus 0.3 yt and then plus 0.3 expectation of yt given only information of xt. So this in general will not be 0, okay? Because expectation of yt given information of only x up to t, so that contains some information. So it will not be exactly 0. At the same time, it will not be exactly yt as well. Okay. So it will not be exactly estimated as yt. So this will not be exactly 0. This will be larger than 0 in general. Actually larger than 0. Well, at the same time, of course, MSPE of sorry about that. So this will be plus epsilon t xt plus 1. So let me write one more line. I'm really sorry about it. I just want to include this example. So this will be, because epsilon t x plus 1, so is independent of all the information up to time t. So this will be summed as the another term. When you expand this square. And then plus expectation of epsilon x t plus 1 squared, so which is sigma squared. But this term here already, this is non-zero, so this should be larger than 0. So that's what I want to say. But MSPE of xt plus 1, so this is very simple, so this is just expectation of xt plus 1 minus xt bracket 1, and everything cancel out, okay, so because xt bracket 1 is exactly 0.8 xt minus 0.3 yt. So everything cancel out except the last term epsilon xt plus 1, which is sigma squared, okay. So if I do this explicitly, then you can see, okay, I can see that the mean square prediction error when I don't include y, okay, will be larger than when I include y as an explanatory variable. So I will conclude that, okay, so yt is grandeur causing xt here in this system, okay, and h equals 1. So that much is obvious. Well, perhaps let me calculate something that is a little bit non-obvious. Look back at the system. If I want to say instead of h equals 1, let me consider h equals 2. Let me talk about second step I have forecast. So what is a system? Well, set t plus 2 will equals to what? Will equals to phi set t plus 1 plus epsilon t plus 2. And then if you substitute set t plus 1, so that will be phi squared set t, and then plus phi epsilon t plus 1, and plus epsilon t plus 2, right? So I hope this substitution won't be too difficult. So why will I do that? Because now set t plus 2 equals to something that is with information up to time t. You know what that is. And all these epsilons, the conditional expectation of information up to time t, well, they're 0, okay? So therefore, your xt bracket 2 is phi squared set t, right? That's the first element actually. How to write this? So first element. But what is phi square? So if you calculate phi square carefully, so phi is here. So you need to calculate phi square, right? So phi square is 0.8 squared, 0.64, no problem. And 0.8 times minus 0.3. And then plus 0.3 minus 0.8, that's 0. And then at the same time, so the lower left corner, that's 0 as well. So 0 times 0.8 plus 0 times minus 0.8. And then finally, so it's again 0.64. Right? Okay, so what I'm doing, so phi square is actually a diagonal matrix. So what does it mean? So it means phi square times zt, that is 0.64 xt, right? And it's the first element, so it's 0.64 xt. So what's so special about this? This is special because now, remember, when h equals to 1, when h equals to 1, your xt bracket 1, your first step ahead forecast actually depends on yt. But here, at h equals to 2, the best two-step ahead forecast now doesn't depend on yt. So we just follow the calculation, right? So we made no mistake, so that should be the case. So at h equals to 2, the expected value of xt, in fact x minus yt, I shouldn't say this, okay, sorry. So I should say xt, x minus y, t bracket 2 is actually the conditional expectation, right, of xt plus 2 given the information on x only without y. Well, it's actually, if you use the law of iterated expectation, this is equals to what? This equals to, let's take conditional expectation of xt plus 2 given the full information with x and y together, ft, and then conditional on the smaller set of information, this time without y. That's the law of iterated expectation, okay? So conditioning on larger information set first, and then on the outside conditioning on a smaller set of information. So that's most general form of law of iterated expectation. So I hope I talk about this in seminar. If you are in other class, then take it from here. So why do I do that? Well, because now then, what's the inside? So this inside is exactly xt bracket 2. And I know from this calculation, this is only dependent on x. So expectation of 0.64 xt conditioning on all information of x up to time t, well, that's enough to say this is still 0.64 xt. The importance is, this is exactly xt bracket 2. So without information on y, and with information on y, the forecast is exactly the same. That's the importance of this calculation. So immediately you can say, okay, at h equals 2, it doesn't look like y is Granger causing x at all. So if you're doing first step ahead forecast, well, it is. It is Granger causing xt, but not when you look at second step ahead forecast.
Would we need to check for more steps or a second step?
I'm just asking for second step, then you just need to check for second step, of course. Yeah. But you can see that in this example, so if I look at h equals 3, then you see that again yt is actually Granger causing xt. So at the odd step, y is Granger causing xt, but not at the even step.
For
In this
example, this is
particular
an
setup.
exam question, we'd only need to check for step 1 and step 2.
Of course, I'll give you the steps.
Okay.
Okay. So this has to be specified. Okay. This will be made explicit. So say therefore, of course, the MSPE of xt bracket 2 is exactly the same as MSPE of x minus y of t bracket 2. They're the same. Okay. So one is not smaller than the other, then there's no Granger causality here. So I spent a little bit more time because I know that this is a kind of new concept with many notations, so I need to talk about this a little bit slower. So continuing with this example, so therefore at h equals 2, yt is not Granger causing xt. In fact, so you should be able to see this. So in fact, at odd value of h, yt is Granger causing. But not at even value of h. So it's just a particular example. And the important thing is, so you can see that when yt is not Granger causing xt, the best forecast without the information on y still only depends on xt itself. Okay? Before, if yt is really Granger causing xt, the best forecast actually depends on x and y together. Okay? So this is related to the claim that I'm going to make. And this claim will be general, okay? And this is in the lecture notes as well, this claim, but I'll prove it here. It's not written in the lecture notes. So you're given Wt equals to this system. Now go back to xt, yt, and zt. If set t bracket h does not explicitly depend on anything in xt. Of course, up to time t. Then we'll say xt is not Granger causing set t. And here is conditional on yt. So yt is just a passerby here, explanatory variable. So this basically is a generalization of what we just observed in this previous example. The h-step ahead forecast was set t when we observed that it does not explicitly depend on anything in the explanatory variable xt or any past values, then okay, we say xt is not Granger causing set t. Okay. Well, you can even take this as a definition, but the definition I've just given you is in terms of mean square prediction error. So you need to kind of relate this to the mean square prediction error. Okay, so therefore you need a little bit of a proof here. So it is this proof that I haven't included in the in the lecture note. So let me do this as simple as possible. So this will be so it will be this minus set x set t bracket h in fact, let me make it the most general case. So this is a vector case. So this is set t plus h, sorry. Wow. So it's comparing to the real value, not the estimator. Set t plus h minus this set minus x t bracket h. So basically this is the mean square prediction error for when you don't have the information on x. Okay? For set t plus h. So this is MSPE. How is it related to the other MSPE? Well, we try to take out the set t bracket h and then add it back again. So we form two groups. Okay. And why do we do this? So when we expand this, at least this part corresponds to what? the MSPE when we do the best forecast, including information of the time for X, okay? So let's expand this together, okay? So we're going to expand this. The first is expectation of ZT plus H minus ZT bracket H squared. So as promised, this is the MSPE for the best forecast. So with information up to time t for X as well. And then plus of course this term ZT bracket H minus Z minus X T bracket H. But how about the cross term? Of course there's cross term, so you need to plus. Our cross term again is 2 times. They're just scalar, okay? Whenever scalar, you expand this, so it's 2 times the expectation of the dot product of these two terms, right? Minus ZT bracket H. Dot product means the transpose times the other factor. Okay, sounds complicated, but the cross term actually is 0. So again, how do you see that? You use the law of iterated expectation. So on the cross term here, so let me write the full cross term, okay? So this full cross term, actually using law of iterated expectation. So this time perhaps we can condition on Ft. So the outer expectation is the marginal expectation without conditioning on anything, but the inside expectation, so we can condition on Ft, the full information including every variables available. There's also law of iterated expectation, right? But the inside expectation, so this equals to, I'm running out a little bit of space here, so let me write it a little bit narrower. Now, given Ft, obviously ZT bracket H minus Z minus XT bracket H, they are all containing information of the time t. So this is a constant you can take out. And then the inside expectation becomes what? Expectation of ZT plus H minus ZT bracket H given Ft. This is 0. Why? Well, expectation of ZT plus H given Ft, that's exactly the definition of ZT bracket H. So it's ZT bracket H minus ZT bracket H, that's 0. So the cross term is 0. Therefore, MSPE of Z minus xt bracket h equals to actually the MSPE of ZT bracket h plus this expectation of ZT bracket h minus Z minus xt bracket h. So at least we can link the two MSPE together, actually. Now, finally, we can use what we stated in the claim. So if set T bracket H does not explicitly depend on xt, then what happened? Then what happened is sorry, I shouldn't. Okay, give me 2 more minutes, that's done. So ZT bracket H here is actually the expectation of ZT plus H given FT I should the other way around. So let's look at ZT minus X actually. So let's look at minus X here. This is minus X. So the Z minus xt bracket H is equals to, if you use the law of iterated expectation again, so that will be conditioning on the large information first and then the smaller amount of information. So that equals to expectation of ZT bracket H. Yes. But what we state here is ZT does not explicitly depend on XT. So this one is actually a constant still. So ZT bracket H. So ZT bracket H is actually equals to Z minus XT bracket H. So this information actually tells us that if ZT bracket H does not depend explicitly on any information of XT, then both forecasts will be equal. Now, both forecasts equal, that means what? Using the first line here, the two MSPE are equal. So equal in MSPE, that means what? That means XT is not Granger causing ZT. Conditional on YT at H step ahead. Okay, so that's the end of proof. So that's a. So you need to know this general formula for actually the MSPE of the restricted forecast is actually linked to the MSPE of the full forecast, but plus some other terms. Okay. So that's the main thing that you need to know, and then depending on what condition, so you can talk about this term actually being zero. Okay, so I'll give you 5 minutes. So please come back at 14:11. So we'll continue with the second part of the lecture.
systems, but
And how are they?
just classic mom and dad. With the mom's a bit of like an almond mom. So I'm like,
But I can see how she would be the result of an oven.
I can too, but I'm interested to see how intense of an almond mom she is. That's why I'm
How long are you going for?
just a week.
For a week with another family, can we switch?
Yeah.
Okay. So I'll continue with the grandeur causality. So for a little bit more. So we've talked about some very theoretical ideas of grandeur causality. So it links from the definition of grandeur causality using mean square prediction error to actually about if the best forecast actually depends on certain explanatory variables or not. Okay, so and these two definitions becomes equivalent with the proof I've just given. Okay, so but the definition is still in terms of MSPE, especially nowadays people talk about a nonlinear model and stuff, so they still use MSPE to talk about as a first principle of the definition of grandeur causality. Okay. And so in practice, how do we actually know these kind of grandeur causality exists or not? At least in these linear models, in this vector armor model. So we can actually use the fact that this is a linear model actually to do an F-test. Okay, so we can talk about linear regression. So now set t is the response variable, right? So we can regress set t on xt, yt, and the legs of set t itself. So basically regress on legs of set t, legs of yt, and legs of xt. Okay. So this can include all the legs of set x and y. Okay. And at the same time, we can consider a restricted model. So this red here is means the restricted model. So the restricted model is to regress set t on the legs of set t and yt only, but without any information on x. So we don't regress on x. So that's a restricted model. Okay. So you can regress that and calculate the residual sum of square of the residual of the restricted model and the full model. Okay. So this word actually means reduce, I think, when I first write that. So reduced model and a full model. So the reduced model is without the effect on x. The full model is with the effect on x. So the residual sum of square of the reduced model certainly will be larger. It is definitely the case. So is this larger residual sum of square minus the full model's residual sum of square divided by its degree of freedom. So if the reduced model has R parameters and the full model has S parameters, then the degree of freedom is S minus R, the difference between their number of parameters fitted in the model. And then divided by the full model, RSS full, divided by its degree of freedom. Degree of freedom for the full model itself is the sample size t minus the number of parameters in the full model. Okay, so this is linear regression. This is exactly following the linear regression. Okay, in the F-test. Okay, so under certain restriction, even for time series model, so this F-test is valid. All right. So if you don't know too much about F-test, so maybe have some reference for undergraduate tests involving linear regression and testing of sequential testing of linear models. Okay, so this is, I think, in that well, right? Yeah, F-test. F-test for restricted model and a fuller model. Okay. So we borrow that F-test to here. So your H naught is, your xt is not Granger causing ZT, conditional on YT at a certain H. And alternative is, of course, is Granger causing. So if it's not Granger causing ZT, then the reduced model and the full model shouldn't have too much difference in the residual sum of square, right? That's the idea, so that f is small. Under alternative, f, the value of f should be large, okay? Under H naught, f should be small. What is small? Small is governed by this f distribution, right? So, yeah. So you saw f distribution of degree of freedom s minus l and t minus s to see if indeed the alternative hypothesis that of Granger causality is correct or not. Okay, so I'm not writing this down. It's just some practical thing that you can use, and I even include the code here. So this code can be downloaded in the Moodle page or our scripts. So you can see the Granger causality test.r. So this everything is in there. So I've copied it here. So I've included the example in the lecture notes. So you can see that in the lecture notes I have an example 4.8, which shows you a complicated vector AR1 model, okay, for WT. WT include XT, YT, and ZT. And so my question is, so does XT Granger causing ZT at a certain H step ahead? So I'm presenting this analysis in this example, and also give you this code to generate this example. So if you, so let me run this very quickly. So this example is basically very similar to the lecture notes. Okay, so I'm just having x as the first series, y as the second series, and z as the third series considered here. So you can see that what is P1? P1 is the phi 1 matrix. This is a vector AR1 model, okay, with this phi matrix equals to defined by this, okay. So I need to wait for it to finish to show you exactly what this phi 1 matrix is. This sigma is actually the variance covariance matrix for the epsilon for the noise, okay. So it doesn't matter too much. Theta 1 here, so this is basically simulation of the vector armor model. So theta 1 is the MA component. So the MA component, I put it as 0, okay? So they are all 0. So it's just the vector AR1, okay? So let me, so finally I think I can run this. All right. So we generated some plots here. Here, plots doesn't matter too much, but is xt Granger causing set t here, conditional on yt? Well, you look at the P1 matrix here. The P1 matrix is, well, certainly not symmetrical, so there's no reason for it to be symmetrical. Okay, so this matrix, you can see that the upper corner of this matrix is 0, so just as this example here. So I'm basically replicating example 4.8 here, okay? And theta 1 is 0, so it's just vector AR1 model, okay? So sample size is 500. So it should be the case that when h equals 1, then is actually xt is grandeur causing set t, right? With this definition. So how do we test it? Well, you can use this code here, which is basically doing the linear regression with the full model and the restricted model. Okay, so we can run this grandeur causality test. So order equals 2. It means that we include legs of z and legs of y and legs of x up to xt minus 1 and xt minus 2. You can include more legs. Okay, you can include more legs. I include order equals to 2. And all these, you can check the code yourself. So you can see the full model. My set is regressed on the legs of z, legs of y, and legs of x. For the reduced model, I'm just regressing the set with legs of z itself and legs of y, but without information on x. Okay. So let's do this. And take the degree of freedom as well. So the degree of freedom is given actually in the data. Okay, so you can see them. For instance, the degree of freedom for the reduced model is 493. Why is that? Well, there are 7 parameters. Okay. 7 parameters in the reduced model. Okay, so the mean itself, the legs of z and legs of y, so added together, there are 7 parameters. So t minus 7, t is 500, and then minus 7, that's 493. So for the full model, so the degree of freedom should be smaller, exactly 2 smaller, because including legs of z, x, I initially said the order is 2. So if I include the information in x, I include 2 legs of x, so 2 more parameters. So the full model will have degree of freedom exactly 2 less. Okay. So then I can calculate the f value. So it shouldn't be too difficult. The value of f is not important, it's the p value that's important, right? So we compare to the f distribution with this p value. Okay. So remember what p value is. P value is the probability of getting at least as extreme the data at hand, okay, under the null hypothesis. Okay, so under the null hypothesis, the probability of getting at least as extreme as the data at hand is a half, so not too small. That means what? That means probably your H0 is correct. That means your xt is actually grandeur causing set t, conditioning on yt. Okay, so that's the whole premise of this hypothesis testing using f distribution. Okay, so on the other hand, if p value is very, very small, that means what? That means usually that means your data is really, really extreme. If under H0, okay, that means probably your H0 is not correct. Okay, probably the grandeur causality is actually the other way around. Okay. So I think this example is exactly following this example. Okay. And we are testing at h equals to 1. So xt indeed is not grandeur causing ZT. And our null hypothesis is exactly xt is not Granger causing ZT. So the p-value is a half, so not small. So we should conclude that, okay, so the xt indeed is Granger causing ZT, which is the case, of course. We know the simulated model, right? xt indeed is not Granger causing ZT in this model because of the special structure of this matrix. Okay, but how about this is testing h equals to 1 only. H is not the order. Order means you include how many legs in your regression. But we're still testing h equals to 1 only. So how to test h equals to 2 or 3 or general h? So you need to do something about the definition of this response variable. Set res is the response. Set reg is the explanatory variable, right? See, the explanatory variable is just one leg behind this response variable. That means h is 1. So if h is larger, that means you need to maybe a higher order and maybe a larger value than 1 here. So maybe order plus 2 for h equals 2. And then set reg is order to length set minus 2. So as long as set res and set reg is 2 legs apart, then you are basically doing this test at h equals 2. So try to do this at h equals 2 and see what happens. Okay. At h equals 2 onwards, this p-value should be much smaller. Because at h equals 2 onwards, well, generally xt is now Granger causing ZT. So it's example 4.8, okay? Example 4.8. If you do p1 square, matrix multiplication, yeah. So p1 square, you can see this is not 0 anymore, so it's minus 0.66. So xt certainly is now Granger causing ZT at h equals 2. So at h equals 1, no Granger causality, but at h equals 2, certainly there's Granger causality. So try to do this f-test again, okay? So I'll let you do this, all right? Yeah, I know it's a new topic, but I will not have too much time to talk about that. So, but you need to remember the proof, okay? How to link the mean square prediction error proof of Granger causality, the definition of Granger causality, to dependence on the time series on xt explicitly. Okay, so the two definitions will actually be equivalent to each other because of the proof. So you need to understand that, and also how to set up this f-test. Okay, so you need to with this example 4.9 as well, how to set up the f-test. Okay, any questions? So of course, there are some very restrictive condition for this Granger causality. So this basically is confined to vector armor model. Okay, so this f-test at least is confined to vector armor model. So and linear effects only. So when you're talking about linear model like this, so it's sensitive to heavy tailness of the data. That certainly will be the case. So, confined to linearity, so people nowadays, well, their extension to this Granger causality to nonlinear, more general time series models, and robustness as well, robustness to heavy tailness. Some is robust to even missing data. Okay, so there are lots of things that people have done on this in this regard to try to generalize to this grandeur causality definition. So if you're interested, have a look. So you can ask me to give you some pointers if you're interested. Let me know if you have any questions. Okay, but otherwise, so I will skip writing down this seasonal Varma because I've given you already seasonal ARIMA model, okay? And this seasonal Varma is just a direct extension to multivariate setting, okay? So I will not examine you explicitly this model, okay? I'm just writing it down to show you, so there is something of multivariate nature for this seasonal ARIMA model, okay? And why I don't do this, why I don't formally introduce this, because even model 4.37 becomes problematic when you extend scalar time series to multivariate time series in this seasonal setting. The first problem is, well, you remember, hey, there's a product of this backward shift characteristic polynomials, right? Now it becomes multivariate. The order of this product matters. So all this order of these products give you different models actually. It gives you completely different models, to be honest. Okay. Yeah. So even defining it is problematic. Okay. So I'm not going to touch on this. Okay. In this course, I'm just writing one of the form of the model down, and then tell you that there's some problem in it. That's it. And this example 4.10, so is basically using this multivariate model to try the seasonal Varma model to try to model the multivariate data. So multivariate in the sense that not only including London, but also in different regions, so Yorkshire, so Eastern, Western, Midlands, okay, etc. So 9 different regions, including London. So it's a 9-dimensional factor ARMA model at seasonality equals 12 being considered. And you can see that the model considered is not very well fitted. So you can have a look. It's the how price dot R. So this is the general factor. So you can see the S Varma model. Okay. So you can see it's really difficult to find a good fit for this seasonal factor ARMA model. Actually, notwithstanding the problem of even writing down the model itself. Okay. So even if this ambiguity is solved, which is not, okay, by the way. So even if this is solved, multivariate model itself is surely very difficult, especially when your dimension is 9 here. Dimension 9 means what? Means all the coefficient matrix is 9 times 9, there's 81 different unknown parameters. Just for one coefficient matrix, okay. There's really a lot of parameters to consider in a simple model for 9 variables, okay. So it's no wonder. So these models, how to say, don't really attract much attention because it's difficult to find a good fit for even a small dimension like like 9, okay? And if you compare this, so try yourself, okay? So you compare this seasonal farmer model to the fit just for London, so you can see the complexity of this seasonal farmer model is much simpler than just the scalar model, just the scalar seasonal ARIMA model for London. And the reason is we don't have enough data to consider a more complicated farmer model. We just simply don't. Remember, the sample size for this data set is what? 300 something? It's very small sample size compared to the number of parameters you're going to estimate. So if you just consider a vector ARMA model of p equals 2, seasonality p equals 1, then you have way more parameters than the sample size already. Okay, it just won't work. So in practice, especially in economics data, where the sample size usually is not that large, people don't really consider this model that much. They just cannot fit this data. So it naturally follows to the final chapter of this course. So if you're, so with dimension equals 9, well, it shouldn't be a large dimension at all. So just 9 different time series. So how about if you look at these different financial time series data? So there are hundreds, even thousands, okay? So that's and even thousands, we will say is just medium dimension, right? Compared to maybe sample size of thousands, tens of thousands. So large dimension is when the dimension is much larger than the sample size, okay? So even small dimension, this vector ARMA model doesn't work. So how can we reduce this dimension? How can we perform analysis of this large dimensional data? So one thing is perhaps we can find some way to reduce the dimension. So we can find some statistics which is valid for large dimension as well, which is certainly one way to do that. So it is test specific and is statistics specific. Here in this chapter 5, I will go for another very important route, especially for time series, is to reduce the dimension of the data itself. What do I mean by reduction of dimension of data? So I mean finding some meaningful representation of the data, which is smaller dimension. For instance, if the house price data, so there are 9 different variables, 9 different regions, can I find some meaningful index for these 9 regions? For instance, perhaps these house price data, they follow similar trends. If you plot them, so you have the data, you certainly can plot them, so you should see that they indeed follow very similar trend. Similar ups and downs, similar trends. Perhaps just one index of the data will do, can represent their ups and downs. Okay, at least the microscopic part, hopefully. So perhaps just one housing index, let's say, can represent these 9 different regions. Then if it's just one housing index, okay, so then yeah, we can go back to fitting this seasonal ARIMA model for a single dimension. That's much easier to do. So that's the dimension reduction, okay? So how to find representation of this large dimensional data, okay? So one way to do it is via factor modeling, okay? So it's factor modeling for time series. So this one, I will again write down something. So let's do this. see how much I can cover. Not too much, I think. Okay, page 6. So factor modeling. For multivariate time series, so MTS is multivariate time series, same as the package. So if you, so I've introduced this, so consider this factor, I'm a P model. So if xt is d-dimensional, and then phi j is d by d-dimensional, so if xt is d-dimensional, then the factor AR model will have phi j as coefficient matrix which are all d by d. So it implies that, so it's a p-dimensional, if it's order p, then it's the p times d square, unknown parameters. To estimate. And p times d squared can be huge, okay? So, for example, if p is 3, d is 100, so p times d squared is what's this? Oh, 30,000, right? There's extremely huge number of parameters to estimate. It's not viable, okay? So we'll consider, are there any meaningful or common dynamics now these common dynamics will drive all or majority of the different time series you're looking at. So let's say xits. I from 1 to d, so that d different time series you're looking at, x1, x2 up to x dt. If we can do this, we call them common factors. So if exist, then we call them common factors. And how to find these common factors? Well, we look at some very simple example first. So, okay, let's say f1t and f2t are common factors. And say, let's say d equals to 100. And what I'm talking about is, so x1t will depends on these common factors, so perhaps linearly. And then the second time series, similar, but maybe with different coefficients, a to 1, and then plus a to 2, and then plus another error. So all the way down to x 100t equals to a 101 f1t plus a 102 f2t. So you may think, okay, so perhaps it's a little bit restrictive, it's just these common factors are linear. But remember, we only observe the original data x, okay? So we're basically talking about effective decomposition of the data x itself. And the common factors, I don't know. I want to find it, okay? So usually linearity suffices in this case. So we want to find latent factors that represent the original data x the most, okay? So usually linear makes sense. Now we can write this as a system. So x1 t, x2t, all the way down to x100t. Let's say this. Let's define this as a vector xt itself. And in this system, well, I hope at this stage it's not that difficult to see that this can be written in the form of a matrix. So a21, a22, all the way down to 101, 102. Sorry, this is 100, okay. And then multiply with just f1t and then f2t. So perhaps we can call this matrix as A. And we can call this the ft. Of course, plus the error, epsilon 1t, epsilon 2t, all the way down to epsilon 100t. So let's define this as a factor epsilon t. So if you want to write this in terms of a matrix form, so you can, it will be xt equals to matrix A times the factor ft, and then plus a factor epsilon t, okay? So it's a, so let me do it generally. So it's a d by 1 dimension factor, and A is d by r, f is r by 1, epsilon t is d by 1 again. So we usually assume that r is the number of factors, okay, is much less than d, okay. So r equals to number of factors so usually much less than the original dimension d. So that's the notation, okay? So this is a linear factor model, or in different fields, so in econometrics, so people call it multi-factor model. It's the same thing. So in a linear factor model, or multi-factor model, so A is what we call the factor loading matrix. So the Aij are factor loadings, and the Ft is the factors. Okay. So epsilon t is just noise. Econometrics, people call it idiosyncratic noise, but we won't even go that deep. Okay. Okay, so several more minutes. So if we write, let's look at this, okay. So if we write this matrix A equals to factor A1, factor A2, all the way up to factor AR. The example here given is R equals 2, right? So this matrix A has 2 columns. Okay. The first column is A11, A21 up to A101. The second column is A12, A22 up to A102. Now if I have R different factors, so there should be R different columns in the factor loading matrix A. So this should be a D by R matrix. So AI contains the loadings for the I factor. FIT. So what do I mean by the loadings? Okay, so because your xt actually can be written in this form. So this is a multi-factor form. So if xt is written in this form, then you can see that how the I factor is affecting xt. The I factor is affecting xt through these loadings in AI. Okay. So if the loadings are large, then FIT may be affecting xt in a larger magnitude. If there's some loadings very close to 0 or exactly 0, then FIT is not affecting those corresponding elements. Okay. Let's say if the first element of this AI is exactly 0, that means what? That means the first entry, x1t, doesn't depend on the I factor, FIT. Yeah? So the loadings has meanings, okay? When it's small, that means the corresponding factor is not really affecting the corresponding entry in xt. Vice versa, if it's large, then it's affecting a lot, okay, the dynamics. So a factor ft, so this is the final sentence, okay, is called pervasive. So if you do economic research or using factor models, so this should be a very common term. What is pervasive? If the majority of the elements in AI, this factor AI are non-zero. Well, if this factor is exactly all 0, that means what? That means FIT is not at all affecting xt at all. Okay? If there's only just small groups of elements in AI that is non-zero, that means FIT only affect a small group of entries in XT. Pervasive means what? Pervasive means FIT is affecting most of the entries in XT. Through the fact that most of the entries in AI are non-zero, okay? So that's pervasiveness. In most economics paper, you see when they deal with this factor model, then okay, we assume all the factors are pervasive. That's what it means. Okay, so I'll see you guys in the next lecture. Okay, we'll continue with factor model in the next lecture. Okay.
Doing my dissertation. This is just, it's actually interesting doing the data science stuff. Right, basically. This comes as second nature.
Oh, that's page 6.
No, look at that, that's kind of well.
The scaling and transformation should be done after you
You still write that.
It says it. Yes, but we didn't do that. Just,
Yeah.
so,
I was thinking that.
because
But we
I
do have
started.
the other data, we have the data set. And scale it.
I just, I
I
don't know
can
how to.
scale and transform the target anyway. You didn't do that.
Yeah,
Yeah.
so, like, I
I don't know.
really don't know how to. Because I said, oh,
You do it.
thing is, all of them didn't know.
You can't
That
scale
you-
the target.
So that we don't scale before
You
the
split.
split. Because then the scaling influences.
Yeah, that's true.
different.
Yeah.
So I think you do this.
Literally trying to see what that says.
I mean, I think it's, I can find out, oh, I can find out on it.
Absolutely, if we think that. But we do
But
have,
then we need to just.
that's fine, because we have, no, we didn't, because we have the untransformed, unscaled data.